Greetings and welcome to another episode of Alfredo's Code Along. So, last time in our process of making a chess engine, we already have a good foundation of the structure, the base structure of a chess engine. We have all the moving pieces, all the functional pieces, and have all of the basic functions of a chess ready. Obviously, there's no fancy en passants or, I believe, there's some other fancy moves, but so far it works. And that's all I really need to get started on the next part of the project. So right now you can freely move any piece you want at any time or any turn. There's no sense of game rotation. So let's add that right next and have the computer or the chess bot respond to our movements. So quickly we want to add in the variable that tells us if the game has started. Call it game start. So initially it's false. And then at the end of each of our move, we want the chess bot to respond, which will simply just be, we check for if the game has started. If so, we ask the chess bot to return a move, which we'll just call a move, and we'll get it from the C# code. So we don't have the C# code yet. We will be making that right after this. So let's make a node and create something called a chess bot. Lovely. And then we attach a script to it, call it chessbot. Okay, we'll come back to it in a moment. And now we just say chessbot. Also, don't forget to add in a reference, like I always do. Good for housekeeping, and in case you have a more complicated structure and move nodes or scenes around, it's better to have them referenced instead of using a direct directory. Okay, so now we have a chessbot that to call some function. We don't have it yet. Let's just name it find next move for now. Okay, so after that, we want it to return some sort of a move, which tells us from where to where. Since chess doesn't have overlapping pieces, luckily, we can just use two locations to indicate a move. And then we'll just use a function in Godot to move the display. It will take in the from position and to position. And same thing, because of my mishap from a couple episodes earlier, I'll have to reverse the move index, but this is not a very big issue. Okay, so let's quickly make the update board. It's going to be similar to move piece, except it takes in a different parameter. And really is just me not planning ahead and unwilling to change things midway. This gives you a valuable lesson. Plan ahead when you're making larger projects like this. Okay, so we just quickly do that, and in fact, I'll be right back with the completed results. Okay, just like the move piece, we check for some extra pieces. For example, the extra check here is if the end piece or the capture piece is the king, we no longer need to continue the game. Other than that, it's the exact same. We take out the piece in the end location, and then we move the piece, and at the end, move the piece from the start location to the end location. Simple as that. Now we can move on to our C# code. So what do we need to have in the C# codes? We need to start a few things beforehand before we can start the chessbot. First, let's go to the data handler and create the move I talked about earlier. Just use it as struct. Call a move. And just have two variables. just for housekeeping. And just give it a quick initialize. And set it to the values we pass into it. Okay. The initializer is done, and let's go back to chessbot. Alright, so remember in Godot, we asked for a specific function or method that we don't have yet in our class. Let's give it that. We'll have this find next move function. So going to be returning a int array, which is the move from location into location. Takes pretty much nothing. Okay, so a few things we need to do when we search the bot. First, I'd like to have a way to track how many nodes I've searched. So in that case, if something unexpected happened, we know where to check. And let's put that as a variable. One from different languages really messes me up sometimes. Start at 0. And at the start of it, we clear it because we need to call this over and over. Okay, and then let's have another variable as a setting. So this one is the max depth. It determines how much we are searching for specific code or for a specific move. The deeper you search, obviously, the longer it's going to take. So for now, let's set it to just 3. Okay, just for testing. Now we can actually put in the search function. So what we're going to use is a classic MiniMax algorithm to search for opposing agents, which I'll just put it right here as a placeholder for now. Call it search moves. Do the exact same. Okay, it is going to be just a dummy function right now. And let's see what exactly we need to put in there. So it is a search algorithm, obviously. I'm sorry. Basically, we're going to call it here and then have a few things. What color, I believe, we need to know about. Right, so is it black move or white move? Since we're going to, for now, let us be the white and the enemy be black, we're always going to make this true. So the first parameter is going to be is it black's turn, and let's say it's true. Okay, and let's think for the next parameter, we're going to need something to limit the search, which is going to be the depth. And here we would just put in max depth for my initial search. Right, that will do. And then we need a current board. So what it looks like in the board right now. And I'll just put in current board. And let's create that in here somewhere. Okay. It's going to be a bit board. Call it current board. And then have something to set it up. Call it bitbot. The bitboard. And current board. That'll do. So basically, this sets the current board of the chessbot to the bitboard, which is synchronized with the one that is displaying in Godot. Very great. So this will be the initial input. Although in the algorithm itself, there will be additional parameters, which implements the alpha-beta pruning. Without it, it's going to be painfully slow. So the alpha and beta are effectively a cache value of the max and minimum valuation of different agents. And the initial value can just be one setting to minimum and one setting to maximum, but the opposite way. So I highly suggest taking a look at what exactly a MiniMax algorithm is and how alpha-beta pruning works, because if I try to explain this video will be much longer than desired. I will give you links to videos and explanations that explain these concepts way better than I do. Okay. So now that we have the setup, did I set it to, oops, bad. I forgot to give it bitboard, the current search board. Everything's in place. Good. Now let's create the return value, which is the next move we're going to go back, which is just current move. Right, we did not create this yet, so we go do that. The current move is just a move from the struct we created earlier. Going to be a public data handler dot move current move. And when we create it, we can just initialize it to something that definitely looks wrong if it wasn't set properly. Okay, let's see, where were we? Yes, current move dot from and current move dot. Okay. And we want to update the current board as well. So we have make move, which will move the chess or the bitboard inside this part, the saved current bitboard, with the values we got from the bot. The make move will obviously use the current move. All right, let's quickly make the make move function. Okay, to do the make move function is rather simple. We just make a quick function, take in the move struct on move, and then we want to know which side is moving. And if it was black, we take the from list as, well, black. And if it was white, it's the opposite. Simple as that. Same thing with to list. We can just copy this, type it again. And we just switch them around. Okay, lovely. Now we first delete everything in the destination square. We can just do from setting up a dummy bit, is just one oolong, and then move it to however many grids from is. Right, and then we also get a 2-bit. They're basically just a single one in the 64-bit representation, and just put in the correct position. Okay. So to delete it, we just do a simple for loop. I'm too lazy to think of a better way to do it. So if you can think of one, make sure you do it yourself. Alright, so just do that. And we want to take it out from the to list, the destination list. Right, and then we just end it with the inverse. The end, there's this. Okay. Now that deletes the corresponding bit from the destination pieces. And then we can check if which piece type is being moved. Right, delete it, and then take it from and add it to the destination. Sorry. So you just do the exact same thing here. If we see that from list, and from bit, so we check if there exists the bit in there. It basically loops through each individual pieces to see where exactly it's which piece is moving. So if we find that overlap, we go and move it. List. Just end the reverse that. And we take it from, or we add it to the from list. Yes, because we want to add it to the whichever piece you're moving, which side you're moving from is where you want to add the result piece. So I probably made a pretty bad naming scheme here. Either way, you should be able to see the logic. We take out the piece from the enemy side, if there is any, and then we check for which piece type is being moved, take that piece, remove it from the original spot, and add it to the new spot. Simple. Okay. Now we can go back to ChessBot, I believe. Why does it not see make move? Oh, right, because we also told it which side is moving. And since for now we're using just black, we're letting the computer bot take the black side, we'll just set it to true. But if you want to take a different side, just set it to whichever side you want to be. Okay, where were we? Yes, bot. Yes. Okay, so after we're done with moving the bitboard inside C#, we can just return next move back to Godot. And at that point, I believe it will just update in the scene here and update the GUI so we can see what happened. All right, now to implement the actual algorithm. So before this, we need a way to evaluate the goodness of a certain scene. What do I mean by that? Well, you want to be able to look at a board and see, well, which side has a better move right now, which side is winning. Right, the computer wants to know, after it made a move, how good that move can be. And the first thing that jumps to your mind should be, well, how many pieces does the side have currently on the board, and what type of pieces they are. Right, so let's make a evaluation function that calculates how many of each piece is left, and assign it each piece with a value, and then calculate the total. Okay, so in that case, evaluate. First, tell us which side is moving currently, which side we want to check for, and then we give the search board. what board is the current state in. All right, so the values we want to have is how do we want the values? Okay, let's just save the value somewhere first before we use it. We're probably going to use fixed values for piece values. And since it's my habit to put everything into data handler, let's just put the piece values in data handler. And let's just use the conventional piece values of how valuable things are. Do I officially agree with these? I don't play chess enough to give a second opinion, so let's do that. So we will use the order of bishop, king. We'll just give king a very, very large value so that it's disincentivized to lose it. Knight is also 3. Pawn, each pawn is worth 1. Queen worth a lot more, of 9. And rook, give it 5. Okay. Now we have that. Go back here, make a data handler class so we can actually use it. But I'm doing this way. Call it. I really need to work on my C# skill after this project, but for now I think it'll work. I believe it will work. Alright. So we want to calculate the white values. White values equal to a way of gathering up the values. Let's see. Okay, so we will need a second function. Let's call it piece values. And we'll just put it right here. For the benefit of doing it separately, the piece values from evaluate function separately, is so that you can add in other ways to evaluate just right after it. Right. So for this, we'll just use pieces. Okay, what we need in there, we need the bitboard's pieces, which is just these, right? These pieces. We can take that from the search board, right? The input will just be search board dot, well, the type of piece you need. Actually, for this one, I think you just need the search board. Yes. Okay. So for white values, we're obviously going to put in the white pieces. For black values, we just use black pieces. Makes sense. Black values equal to piece values. And search board, black pieces. Good. Okay, to calculate the total pieces, or the total values of each piece, we just do this. Total value is started with 0. And then we just do a simple loop to calculate each of the Ulongs, which is done simply from looping 6 and 5 plus. And I can just do it with a one line of doing. I'll use a pop count. So every time I see a 1 bit, I'm going to multiply it by the piece value and then add it to the total value. Which I think bit operations is the one I need. We'll do pop count. And then we'll take for each piece with a loop from it, like all the pawns, the pawn bit board, and multiply it by the piece values of that respective index, the pawns. Okay, let's see why it is screaming at me. Did I miss a parenthesis somewhere? Yes, I did. Alright, so this basically counts how many 1 bit is inside this bit board, aka how many pieces exist for that piece type, and then we multiply by the piece value. And we loop that through all of the values, and then we can just return the total value. Simple. Good. And we repeat that for white and black values, and the evaluation is just going to be the maximum minus the minimum, which is just going to be white value minus black values, and we return, depending on which side it is, a positive or a negative. In tradition, we're just going to use negative for black, and just click is black. Is a black move. For tradition, I think we use negative for black agents and positive for whites. Okay. What did I miss? Oh, first, I did not spell this correctly. And oh, I misspelled this. And okay, perfect. Now we have the evaluations, we can start making the actual algorithm. That took way longer than I thought it would. Okay, but we are in our home stretch. Once we're in the MiniMax algorithm, we can just start searching. Since it is a recursive algorithm, we need to have some exit statement, the edge cases. First one, simple, is if the depth has reached 0. So if it is at 0, we just return with the current board's evaluation. We just evaluate the current board. So let's tell if it's whose move it is, and give it the board. All right, I spelled that wrong in this one too. Okay, so now what we want to do is, in the MiniMax algorithm, we want to generate a list of all possible moves, and then we go through each individual one of them. So how is that going to be done? We need a list of all the moves, obviously. Move. And just call it moves. Okay. What is that going to be? Then we need a way to generate all of possible moves. And we'll just let the bitboard do that. We'll make a function or method in here called generate moveset, and just tell it which side it's currently moving that we're looking for. Okay, so let's go make that. Generate moveset in the bitboard. Okay, this is going to be a bit of a long one, but once we're done with this, we'll be really soon. We'll be really close from finishing. Alright, let's make it. So it's going to be a generate moveset, and let's let the return type be a list of moves. A list of moves, and we'll ask it to take in which side we want to check or we want to generate. Black move. Alright. First, have a few ways for us to tell what we were searching. There's a search list, which one we're searching, and well, first define them depending on which side we're using. Have an enemy board, a self board, and of course a move set to be our return value. Ooh, and then lastly, we're going to invoke an object of generate path so that we can generate each individual path for each individual pieces. Call it path generator. Okay, now we decide what to put into each of these variables. If it's black, is black move. Then we set the self board as blackboard. Remember all of these functions we made in the last episode. White bit board. Okay. And the search list is going to be black if it's currently black pieces we're interested in. And then if it's white, we do everything but the opposite. And we can just that. Okay, and take the blacks here and turn it into white pieces. Okay. And now we generate each individual pieces one by one. So let's first do bishop. Yep. Alright, the way to do it is simple but kind of annoying. You kind of just have to loop through each of the individual pieces to generate for each of them. Alright, so I'm going to loop through the entire board. Check if there is any pieces. What I mean by that. Oh, I put in outside by accident. There. Okay. Whew. So, if inside search list, I will need another parentheses for that because we're checking for search lists of 0, which is where the bishops are, and see if exists, and we'll check that with a dummy bit of 1 bit shifted to the left by I positions. And we're going to check if this is equal to 0. If it's not, that means there exists a piece in there. And we will do long current moves, current move, current moves equals path generator. And we'll call the bishop path to get the current piece's path. Oh, we put in the position. Remember what we have here for, where is it? Generate path. How does it work? Okay, for bishop path, we want the position, the self board, enemy board, and if it's black. Go back here. Wait, bit board. So I is the current position. In the loop, we put in self board, we put in enemy board, and we'll tell the function if it's black to move right now. All right, now for every move, we're going to add it into the new move and then add it into a new move set. So what I mean by that, simply just do bad naming scheme once again. J++. And let's, all right. We check if the move is a viable move. If there is a viable move in the move VIP board. If it is, current moves and 1 too long of J. Let's see if that's 0. If it's not 0, then we know there is a viable move. Then we add it to the list of moves. New move. Okay. UIJ. So basically, this gives you a a new move from and to location. And then we add that to the moveset. Alright, so once this loop is finished, all of the possible bishop moves will be added to the moveset. And we just repeat that for, well, all of other pieces. And with the exact same process, I'm going to spare you the wait and cut right to it. Voila, now we have bishop, king, knight, pawn, queen, rook, all of them. Okay. And at the very end, we just return moveset. Now, remember why we were doing this? Yes, we wanted the entire moveset of all the possible moves inside a current state of the board. And then we want to go through each of them and do something about it. So what do we want to do? We want to do a for each of the moves. I refuse to type these things again. In moves. Probably not the best way to name it again. Okay, so this basically starts a new node, a new scene, a new board, depending on how you think about it. And then we set the new board to the current move, right? Or the current state of the board. Did I not click the dot? I did not. Board into search board. Dot white pieces. I thought I made this function a while ago. Remove piece, init bitboard, clipboard, blah blah blah. I did not make a set bitboard. I thought I did. Strange. Now let's quickly make that. It's going to be very simple. We will just copy the bitboard over, and we just put it right before the init. So we'll just have a void set board and give it the whites and the blacks. And then since we want to make sure it is not by reference, we'll use a copy. Will be many generated. If it's the same one, it will probably create some bugs. Okay, good, and get blacks, pieces, and blacks outline. Okay, so back to ChessBot, and back to where we were. Board. Okay. And then we want to say search board dot black pieces. Okay, and then we make the move of the current move we selected. Board dot make move. We make the move we selected, and we tell it it is black to move. Okay, and then we do another evaluation. The evaluation is going to be a recursive call of what happens the next move. And since the next move is going to be the different agent, we will use a negative value, and we simply just call himself, call the function itself, and we make sure it is whoever his move is changed. We just flip this bit. If it used to be black's move, now it's white's move. And then we'll make sure the depth is decreased by 1. We pass in the new board. And then we give it the negative of the beta and the negative alpha and change their positions. Make sure the alpha beta pruning is working. Now, after it is returned, either by reaching the end or returning back from the recursion, we'll check. So if the depth is at max depth, which is whatever you set it to, and the evaluation is greater than alpha, this means the maximizing agent has a better value or a better evaluation of the current scene than the saved cached value. Then we want to make the current move to the current selected move, because it is one of the best moves picked. And the reason I use max depth alpha to only set it at the max depth is because only the first depths of the tree or the search nodes are the available moves at the current board, because the future searches haven't happened yet. We can't set that. Okay, and we want to make sure current move 2 is move 2. Okay, good. And then we refresh the alpha values. With whatever is bigger, it's evaluation alpha, so we just use a max. And if evaluation is larger than beta, that just means this node is too good and it won't choose it, thus we can just prune it. Okay, at the very end, we just return alpha after we've done all of this. What is this from? For each, okay. So right here is where we put the return alpha. Now, I believe at this point, the function is complete. Let's quickly compile it and see if there's any issues. Okay, it compiled smoothly. Right, let's give us a start game button to make sure it does something. All right, let's give it a button to tell us what is going on. And we'll call this one start game. All right, quickly make things a little bit bigger so we can see it clearly. For it's a bit too big. 40. Not good enough. Okay, start game button. And then we'll link the signal to UI and do a few things. Okay, so when we click on the start game button, we would like to initialize the board at the current state. Let's make sure everything's cleared. Let's clear the board filter. Okay, and we want to also clear rogue pieces on the board. So let's make a function for that. Call it clear piece array. Don't need it to return anything, so just do void. Just do everything inside the piece array, get rid of it. If I exists, queue free it. And then fill it with just zeros like we did when initializing it. And that should just do it. Okay. So we clear board filter. We make sure there's nothing selected. Even if you were selecting things, just clear it. Piece selected, set it to null. and then we initialize the board by parsing the fence string. We call the bit board and initialize the board. Init bit board with the fence string, same thing. Okay, and then we can just call the chessbot to initialize it. Let's see. I think we have the right function for it, right? Initbot looks good with the bit board we have here. Now they're synchronized, and then we can do a game start. Now, I think that will do it. Let's give it a try and see if it works. Fingers crossed that it's not bugging out. Okay, and correctly. Let's move. Looks like it's doing something.